Alright, so the next problem that we're going to do is problem 32 from chapter 4. You throw a ball to a wall at speed 25 meters per second at an angle that's 40 degrees above the horizontal. So we have initial velocity that is 25 meters per second and the angle is 40 degrees. And the wall is distance 22 meters from the release point of the ball. So D is 22 meters. And how far from the release point does the ball hit the wall? And what are the horizontal and vertical components of the velocity as it hits the wall? When it hits, has it passed the highest point or on its trajectory? So let's draw the diagram. So this is a diagram provided in the book. And so this is where you draw the ball. Okay, so this is where the person is at, and so this is the horizontal distance. So from this point to that point, that's your 22 meters. So we can define this initial point to be 0, and the final position horizontally is at 22, and it throws at that point. And the initial velocity, that's 25. Okay, 25, and this is your angle theta. And so you're asked to find, what is you're asked to find? You're asked to find how far above the release point. So this is the release point. How far above the release point that the ball hit the wall. So what you can do is that instead of define y equals 0 from this point, you can just define the release point to be your y equals 0 as a reference. So you can have the y initial point here is 0. And then here you can say that this is the y, the final height, which we do not know, and you're asked to find. All right, so based on this, so again, whenever you are given the initial velocity, whenever you're given the angle, the first thing you do is to resolve the vector into an x and y component. And as you know, this is a projectile motion. There's the x and y motion. They are independent of each other. So let's see, initial velocity, that would be Vix, so you have your 25 cosine 40 degrees. So what you have here is 19.15 meters per second. And then initial velocity in the vertical direction, that will be 25 sine 40 degrees. So that you have 16.07 meters per second. All right, so you have initial velocity in the vertical and horizontal direction. Look at this diagram again and see what we can do based on the information. You're asked to find the how high above that. In order to do that, you probably need to find out the amount of time for the ball to go from this point to that point. We have the horizontal distance that are given, and you have the horizontal initial velocity. So let me just say that the horizontal acceleration is 0 here. And the vertical acceleration is negative g, as you know. So we can just directly use one of the equations from the horizontal direction. And so that's a final position is equal to initial position plus initial velocity in the horizontal direction times time. So from this, you can just basically calculate the amount of time for the ball to travel from this point to that point. Okay? So we have the final, so that will be 22. That's equal to your 19.15, the horizontal velocity in the horizontal direction, and times time. So what is the time that it requires? So you have 1.148 seconds. Okay, so that's the time. That's the time to go from this point to that point in the horizontal direction and also the vertical direction. Now you're asked to find what is the height above the release point. You have the initial vertical velocity, you have the total travel time, so it becomes very straightforward. You will just use the final position is equal to initial position plus initial velocity in the vertical direction times time minus 1/2 gt squared. So this, we do not know, so let me just put down that as h. So you have your h here, the initial height is set at 0, so you have your 0 here, and initial velocity, that's 16.07 times time, so your time we just found, that is this, minus 1/2 times 9.8 times 1.148 squared. So after you've done the math, you should have your height calculated to be 11.99 meters. Okay, so part A basically asks you, what is the how high above. So the final answer is it is 11.99 meters above the release point. And then you're asked to find what is the velocity. What is the velocity when the ball hit the wall? Okay, we find out the time so that we can easily calculate the final velocity when the ball reaches that point. Now remember, this is a projectile motion. In the horizontal direction, there is no acceleration. So whatever initial velocity in the horizontal direction that you have stays the same. It does not change. Now, in the vertical direction, because it's subject to a negative gravitational acceleration, so there is a change in the final velocity. So Vx is equal to Vix. You can just directly write that down as 19.15 meters per second. Now Vy is equal to initial velocity and then minus gt. So initial velocity, what you have here, let me just be consistent. So Viy. So Viy, you have 16.87 minus 9.8, and then times the time. Time is 1.148. So after you've done this, you should get something that is 4.82 meters per second. Okay, so once you have that, what you can do is that you can express the vector in unit vector notation. So you have the final velocity is equal to 19.15 I hat and then plus 4.82 j hat. Now, if you're asked to find the velocity, which I did not calculate, but you can easily calculate it, that will just be the horizontal component square plus the vertical component square, and take the square root of the sum. So you should get something. I did not have it calculated, so you can calculate that. Now, what about the angle? The angle, of course, again, draw it on the xy plane. So you have your x component, that's positive. You have a positive y component. So let's say this is your theta. So this is your b. Let's say theta prime. So your theta prime. So theta prime here would just be the y component over the x component, because adjacent, and it is opposite over the adjacent. So you have 4.82 over 19.15. So again, I did not calculate that numerical value, but you can easily calculate that on your own. Okay, so the final question that you asked to find is that when the ball hits the wall, has it reached the highest point? Now, one of the things that one of the things that you can use to answer the question is that when you look at the final velocity in the vertical direction, if it is still greater than 0, it means that it has not reached the highest point. Because remember, whenever the ball reaches the highest point, it means that the vertical velocity at that point should be 0. You still have a positive value, which means that it is still going up and up, and it can still go up and up until this value decreases to 0. And then after it passes 0 point, it's going down. So when it goes down, the vertical velocity, of course, will become negative. So there are two ways to answer this question. One is that because the vertical velocity at this instant, when it hits the wall, is still greater than 0, so it has not reached the highest point. Now, the other approach is that you can actually calculate what is the height. What is the height that you reach the highest point, and then see if this h is actually greater than the capital H. Okay, so let's do that. Now, how do we do it? Let me erase this. To reach the highest point, we know that the final velocity here has to be 0. So we can easily calculate, because we are asked to find the vertical separation. We're not interested in the time information, so you can do is that use the other equation that we have not yet used it a lot, which is the Vy squared is equal to Viy squared, and then minus 2 times g times delta y. Okay, so this final velocity when they reach the highest point is 0. Initial velocity, you have this 16.07, you square it, minus 2 times 9.8, and times the separation. So the separation will be h, capital H minus 0, so that's just capital H. So after you do the calculation, your H is equal to 17.17 meters. And this is greater than your lowercase h. So which means that the ball can still go higher, so probably will go like that until reach the highest points. Okay, and it's because there's a wall, so it kind of the ball just stopped there. Okay, so that's problem 32. All right, so the next problem we want to do is problem 33, and let me erase this. We should have a better technology so that, when I say erase, it's just going to erase automatically. I don't have to do it manually. But the technology has not yet advanced to that stage yet. All right, so that's do problem 33. Okay, so a plane diving with a constant speed at an angle that's 53 degrees with the vertical releases a projectile at an altitude of 730 meters. So we know that altitude y is 730 meters, and angle is given, that's 53. And let's see, the projectile hits the ground 5 seconds after release. So we know we're given the time information, which is 5 seconds. What is the speed of the plane, and how far does the projectile travel horizontally during this flight? What are the horizontal and vertical component of the velocity just before striking the ground? All right, so let's look at this. So based on the problem, we should draw the diagrams. So let's draw the diagram. So you have, so let me draw here. So again, this is the x and y axis, okay? And so this is where the plane is located. That is 730 meters above. So we're just going to call this the final position is 0, and the initial position is at 730 meters. Okay, and so you draw this diving like this. So again, this is a projectile motion, typical projectile motion, and the angle that it's making. Let's see, what does it say? Diving the constant speed at angle 53 with the vertical. So the 53 is with respect to the vertical. Okay, so this is your 53 degrees, not this, and this is your velocity. And the velocity, we call that VI. Okay, and VI, so let's see. So if this is 53 degrees, you can actually use this, so that's 37 degrees. Okay, so depending on, it doesn't matter which angle that you use. So if theta is 53, that small angle, that's close to the positive x-axis is 33 degrees. And time information is given. So you're asked to find, let's see what you're asked to find, the speed of the plane. So what is the speed of the plane? And you're given this. So it doesn't seem that you have a lot, you're given a lot of information, but let's see. Velocity is not known. You're asked to find, right? And we know that horizontal acceleration is 0, and the vertical acceleration is negative g. And then we have the time. We have the vertical separation. So it seems that we should be able to find our velocity, because if we let's just use the one of the equations of motion. Let's lay out the equation like this. The final position is equal to initial position plus initial velocity in the vertical direction times time minus 1/2 gt squared. We're given the time information, we're given the vertical separation, so we can actually figure out the y component of this speed. And then, because your angle is given, so once you have the angle, you have the y component, then it becomes easy to find out what is the total velocity of VI, and also what is the horizontal component. So let's do that. So the final position is 0, Initial position is 7:30. This we do not know, and then times 5 seconds minus 1/2 times 9.8 times 5 squared. So after you arrange this, your VIY is equal to negative 121.5 meter per second. It is negative, that makes sense, because this is the x component, which is positive, and this is the downward y component, which is negative. So you should get a negative value. So that's negative 121.5 meter per second. Now let's look at the trigonometry. So if you want to use the this one, so sine theta, you can see that sine 33. If we're using the absolute value, so sine 37, sine 37 is equal to the vertical component, which is this, and because you're using a small angle, because my 33 is supposed to be negative, but I'm using a small angle, so everything has to be positive. So you have in the numerical, in the upper one is this, and in the denominator we have our VI, which we do not know, right? So this is sine theta is basically equal to the opposite value over the hypotenuse. So after you work out this, your VI, you should calculate a value that is equal to 201.9 meter per second. So this is the initial velocity, and that's a total value. You already have the vertical value, so we need to figure out what is the x component as well. So x component is just VI times cosine, and then 37, okay? And so you have your Vx, do we have that? We have 161.24 meters per second. We're going to use this information, although it's not asked you to find it now, but we're going to use this information. So I just calculated here, okay? So you're asked to find, what is your asked to find? You're asked to find what is the horizontal displacement. Now, if we define this, initial position to be 0, and the final position is what you're asked to find. So we can use one of the equations of motion, which is the final position is equal to initial position, and then plus the initial velocity times time. All right, so you do need to calculate that immediately. So you have the 0 here, and then plus the 161.24, and then times the 5 seconds. So horizontally, you should get a value that is equal to 806 meters. Okay. So horizontally, it will have traveled 806 meters. And then you're asked to find, what is you asked to find? The horizontal and the vertical components of velocity just before it strikes the ground. So what is the velocity at that point? Since there's no acceleration in the horizontal, so your final velocity horizontally should be, let me just write here, so your final V, it's very busy here. Let me just erase here. So your final final velocity in the horizontal direction should be equal to your initial velocity in the horizontal direction. So your Vfx is equal to Vix, which is 161.24 meters per second. Okay, it does not change. What about the vertical? The vertical velocity then, because it's subject to a negative downward acceleration, so you have the final velocity in the vertical direction is equal to initial velocity in the vertical direction minus gt. So you have your initial velocity in the vertical direction, which is this, is already negative. So you put down that negative 121.5 minus 9.8 times 5 seconds. So you find the velocity in the vertical direction is equal to negative 170.5 meters per second. Okay, so that's your final velocity in the vertical direction. So in unit vector notation, you would say the final velocity is equal to the initial is equal to the final velocity in x direction plus the final velocity in the y direction. So you have 161.24 I hat, and then minus 170.5 j hat, and unit meter per second. Okay, so now you have the the final velocity expressed in unit vector notation. You have the x component, you have the y component. So when you so if you are asked to find the velocity, then this is how you would do. Again, Pythagorean theorem. So you have the whatever value, the fx squared, and then fy squared, and then whatever value that you have is that. And then also draw it on the x and y axis to see which quadrant it is pointing. Let's say you have the positive x component, negative y component, so your velocity is in that quadrant, in the fourth quadrant. You can define this angle theta and then use a smaller angle notation, use a tangent theta. So your tangent, let's say if you want to find this angle theta prime, so you will have tangent theta prime, absolute value. So opposite is negative the y component, and the adjacent is this. So it's 161.24, and then you can calculate what your theta prime is. Okay, I do not have the numerical values, but those are, you can see that they are just basically magnitude, Pythagorean theorem, angle, just use a tangent, and you have to draw the vector in the x or y plane to see which quadrant is it is pointing, and also which angle that you are calculating. Okay, so that is that. Right, so moving on to another problem. Will be problem 86. And again, let me erase this. All right, 86. In the figure, let's see, the figure. Okay, so you have, again, I'm going to draw the x and y. So you have here, this is your D1, and this is your theta 1, and you have here, that's your D2, and then you have your delta theta, that's given. Okay, so let's see. 86. In the figure, a radar station detects an airplane approaching directly from the east. At first observation, the airplane is at the distance that's 360 meters from the station. So this is your station at the angle that's 40 degrees above the horizon. The airplane is tracked through an angular change, which is 123 degrees, in the vertical east-west plane. Its distance is then 790 meters. Find the magnitude and directions of the airplane's displacement during this period. Okay, so you want to find the displacement. So you have, so this D1 and D2 are magnitude of the position vector. So you have the airplane initial at that point. So you can actually, based on this diagram, you have the magnitude, you have the angle. So this is the magnitude angle notation. You want to express that in unit vector notation. So you have the x and y. So find out what the position vector for R1, and then sometime later you move to this position. So you have the magnitude, and you also have the total angle, because this is your total angle. That's called a theta 2. So then you can easily calculate your R1 and R2, which is the position vector. So let's do that. So you have your R1 that has a magnitude of 360. You have your R2 that has a magnitude of 790. Okay, and the angle theta 1 is at 40 degrees. your theta 2 is your theta 1 plus the angular change, which is 163 degrees. So then your R1 that becomes easy. Your R1 will have 360. Horizontally, that will be cosine 40 degrees, and then sine of 40 degrees. So you can see that your R1 will have a numerical value that's 275.78 I hat. I'm missing I hat and J hat here. Okay. So this is your X component, and the Y component is 231.4 J hat, and in units of meters. Okay, so this is your R1. We can do the same thing for R2. For R2, you have the magnitude of 790, and the X component, so you have the cosine 163 degrees I hat, and then plus 790 sine of 163 degree, and then J hat. Now, because I already changed my theta is in reference to the positive x-axis, so my x component can be easily used. I can just use a cosine, and my y component can just use sine. That's because my angle is defined in reference to the positive x-axis. Okay, so then what you have here is that after doing the numerical calculation, you should have negative 755.5 I hat plus 231.0 J hat meters. So you have the position R1, position vector R1 here, you have the position vector R2 here. So you can calculate the displacement, because displacement is defined as the difference of the position vectors. So your displacement, that's your delta R, which is R2 minus R1. So then you have the whatever R2x minus R1x I hat, and then plus R2 y component minus R1 y component j hat. Okay, so basically this minus this in the x direction, and then this minus that in the j direction. So the final answer is 1031.3 I hat minus 0.4 j hat. So that's a displacement of the airplane going from R1 to R2. Okay, so you have this and that. So what is the dimensional displacement? Again, you have vectors, so that's just 1031.3 square plus 0.04 square. I'm dropping, so negative here. So your delta R, I actually calculate this, that gives you 1031.3 meters. So that's your delta R, the magnitude. The angle. So to find the angle, what you need to do, again, draw it on the xy plane. You have the positive x component, and you have the negative y component. So your vector, your delta R is here. This is your delta R. Okay, and then you can define this as your theta. So your tangent theta, again, you can see that I'm going to use a small angle. So tangent theta is the y component. So absolute value, y component, negative 0.4, and the x component, 1031.3. So what you have here is that your theta is equal to 0.022 degrees. Very small. Okay? So that's basically what you get from this. Okay?